Hi, this is Dr. Habib Ahmed, and I currently work at the Center for Advanced Electronics and Photovoltaic Engineering at International Islamic University, Islamabad. On popular demand, I am hereby presenting a video on how to extract the turn-on voltage for a diode and how to extract the threshold voltage for a transistor, and also how to extract the on-off current ratio for diodes and transistors using Silvaco TCAD software. With that goal in mind, let us first consider the example of a diode. We know that diode is a unidirectional device in which the current only flows in one direction. Under forward bias, the diode conducts, and when reverse bias is applied, there is no conduction. Consider, for example, a silicon-based p-n junction diode. We know that initially, under the application of a forward bias voltage, the current is close to zero, and in the range of 0.5 to 0.9 volts, depending on the acceptor and donor doping concentration, the current starts drastically increasing. And this voltage at which the current starts drastically increasing is called the threshold voltage. Now, here is how we calculate the threshold voltage. We know that in this IV curve, we have the maximum slope over here in this region. So we extend a line from the maximum slope region onto the x-axis, or we can say we determine the x-intercept of this maximum slope. And this point, the x-intercept, is called the turn-on voltage of a diode. So this is the story of the forward bias and the turn-on voltage for a diode. Under reverse bias, the current should be zero ideally, but we know that it's not actually zero. In reality, for non-ideal diodes, for practical diodes, there is still some sort of current that flows through the diode. Consider, for example, a couple of works that I performed during my PhD. So here is our paper on gallium nitride based PIN diodes. These are quasi-vertical diodes, and our work got published in Transactions on Electronic Devices. I did my PhD from Georgia Tech, and my advisor is William Allen Doolittle. So for the quasi-vertical gallium nitride based device, we performed the IV characteristics, and you see that under reverse bias there is still some sort of current that flows through the diode. Although this current is really small, it's approximately, this current density is 10 to the power of minus 10 kiloamps per centimeter square. Similarly, under forward bias, this current density is approximately 1.2 kiloamps per centimeter square. Now, the on-off current ratio is the ratio of the current across this diode under forward bias to the reverse bias, or we can say the maximum current that flows through diodes under forward bias to the minimum current that flows through the diode under reverse bias. Now the question is, what is the significance of the on-off current ratio? So the on-off current ratio is actually a parameter that describes the ability to switch devices, both for diodes and also for transistors. So it's actually the capability of a device to control the current, and it is one of the key parameters of diodes and also of field effect transistors. The more the on-off current ratio of diodes or transistors, the more suitable these devices are for digital applications. So then the question is, how do we determine this on-off current ratio? We find the maximum current under forward bias and divide it by the minimum current under reverse bias. This is how we calculate the on-off current ratio. And I'm going to show you how to do this in Silvaco TCAD, how to extract the on-off current ratio in Silvaco TCAD for different devices. Now let us also consider, for example, a MOSFET. In a MOSFET we have a substrate, and then we have the drain and the source region, the gate, silicon dioxide, and then the metal contacts. And if the drain and the source are n-type, then we say that this is n-type MOSFET. Now initially, when the gate voltage is 0 for this n-type MOSFET, we don't have enough number of electrons to connect the drain with the source. We don't have a conducting channel between the drain and the source. So the current is going to be 0. As we start increasing the gate voltage, and when we apply positive potential to the gate voltage, it's going to attract electrons from the bulk region towards this channel. And there comes a certain point when we form a conducting path between the drain and the source. And the minimum voltage, gate voltage required to form this conducting channel is called the threshold voltage. And here is an example of the QV characteristic of a transistor of a MOSFET, but the IV characteristic, the IDS versus VGS of a transistor, also looks similar to this one. Initially, when the gate voltage is close to 0, the current is also close to 0. But then we start increasing the gate voltage, and then there comes a point when the channel is formed, and this drain current now starts drastically increasing when we apply drain to source potential as well to the transistor. And then in order to calculate the threshold voltage, once again similar to the diode, we find the maximum slope region for this curve, and then extend a line from the maximum slope region onto the x-axis, or we can call it the x-intercept of this IV characteristic. And this point over here gives us the threshold voltage for the transistor. So I'm also going to show you how to extract the threshold voltage for a transistor using Silvaco TCAD, and also how to determine the on-off current ratio for transistor as well. So I have already worked on a few examples. I'm going to show you how to determine the on voltage for a diode and the on-off current ratio for a diode. And then I'm going to show you how to determine the threshold voltage for a MOSFET and how to determine the on-off current ratio for a MOSFET. And then I have another example on a thin film transistor. So I'm going to show you how to extract the threshold voltage and the on-off current ratio for a thin film transistor as well. So I'm going to open the interface for the Silvaco TCAD software, and then I open the programs which I already saved. Let us first consider the example of a diode. Here is the code for a diode. I'm not going to focus much on the structure. I'm going to focus more on how to extract the turn-on voltage for a diode and how to extract the on-off current ratio for a diode. So for this diode, the X dimensions are in the range of 0 to 1 micrometer, and then the Y dimensions are from 0 to 15 micrometers. We define meshing as well for this structure. We basically define a silicon substrate, and then we define the electrodes for this structure, and then we define a doping concentration of 10 to the power of 17 p-type for this substrate, and then we introduce an n-type carrier concentration of 1 into 10 to the power of 19 per centimeter cube from 0 to 5 micrometers in the Y direction. Then we include models for this structure and impact Celb is actually a command used for including the breakdown mechanism for the diode. Basically, it includes impact ionization by including Silvaco model for the breakdown mechanism of diodes. And then we also know that we need to include a method to solve this structure. By using this command, we can look at different characteristics, for example, carrier concentrations, electric field, energy band diagram, conduction energy level, valence energy level, Fermi energy levels, etc. Then we save and plot the structure. And then we output this log file with this name, diode example 2_eb.log. We run a sweep in the range of -5 volts to 3 volts. And then in order to extract the turn-on voltage and the on-off current ratio, we have this part of the code. So we basically saved the IV characteristic of this diode in this log file over here. So we call this log file using extract init input file command. And then in order to extract the turn-on voltage, we use this command extract name is equal to v on. And then we have to determine the x-intercept of the maximum slope of the anode voltage to the anode current. And in order to determine the on-off current ratio, we divide the magnitude of the maximum anode current to the minimum anode current. And then we plot the IV characteristics of this diode. So now I'm going to run the simulation. And since I have posted other videos, detailed videos on how to form the structure of p-n junction diodes and for transistors, so I have not focused on the details of the making of the structure. I'm just focused on the extraction of the turn-on voltage and of the on-off current ratio for the diode, and then I'm going to show you how to perform it for transistors as well. So here is our structure. While the code is still running, I can show you some parameters over here. For example, if I click on contour, then I go to define contours. Instead of absolute net doping, I'm going to click on net doping, and then I click on apply, and then I click on OK. So now we see that for this p-n junction diode, we have an electron concentration of 10 to the power of 19 for the n-type region in the range of 0 to 5 micrometers. And then in the range of 5 to 15 micrometers, our carrier concentration is approximately 10 to the power of 17. Or we can go to display, define contours. Now you can see more clearly. The purple color shows a whole concentration of 10 to the power of 17 per centimeter cube, and the red color shows a carrier concentration of 10 to the power of 19 per centimeter cube. We can also look at other parameters. For example, I'm going to show you how to look at the energy band diagram of this structure. So I go to display, and instead of net doping, I want to look at the conduction energy level. I'm going to minimize this. The valence energy level, the electron quasi-Fermi level, and the hole quasi-Fermi level. Click on OK. So here you see the energy band diagram of this p-n junction diode under thermal equilibrium. And now let us look at the IV characteristic of this diode. So I want to look at anode voltage versus anode current. Hit apply, click on OK. So here you see the IV characteristics of this PN junction diode, and we see that we have the maximum slope around this region. So if we extend it onto the x-axis, we see that that its turn-on voltage is above 1 volt. To be more exact, here you can see inside this window, which gives us the runtime status of the program. Okay, so the program exited for some reason, so I'm going to simulate it once again. I don't know what happened there, but I'm going to quickly open the file, desktop, for a diode, and then I'm going to run it once again. Here is the runtime status of the program. Once again, I can show you the steps how to look at the doping level. So I click on contours, and then define contours. Instead of absolute net doping, click on net doping, linear, hit apply. So now we see the N-type carrier concentration region and the P-type carrier concentration region. And then we can look at the energy band diagram of this structure. So I click on Tools, draw a cut line across the interface. Here we see the net doping, where we can look at other parameters as well. As already discussed, the valence energy level, quasi-Fermi level, conduction energy level, the whole quasi-Fermi level, hit on apply. So here is the energy band diagram of this structure, and we minimize this to see the progress of the program so far. So it's running around 1.3 volts, and it's gonna go up to 3 volts. So we are getting there. Then here we want to look at the anode voltage versus anode current. So I click on these parameters, and I don't like the stars on the plot. So then I hit apply, click on OK. Here is the IV characteristic. And we know that here is the maximum slope region for the IV characteristic. So if we extend it onto the x-axis, the turn-on voltage would be above 1 volt, around 1 volt. And we can also see it inside the runtime status of the program. We have extracted the turn-on voltage given over here. It's around 1 volt. And also we have extracted the on-off current ratio for this diode, which is approximately 10 to the power of 16. Or in other words, we can say that there is a 16 orders of magnitude rectification for this diode structure. So I zoom out on this IV characteristic once again, and I go to display, log, hit apply, click OK. So here is a semi-log IV characteristic for the diode structure. The minimum current point is over here. Here is the current under reverse bias voltage in the range of 0 to minus 5 volts. And here is the IV characteristic of the diode structure in the forward bias region from 0 to 3 volts. Now from here we can see that the minimum current is around 10 to the power of minus 19 amps, and the maximum current is around 10 to the power of minus 3. So there is a 16 orders of magnitude rectification for this diode structure, which we can see from the plot, and it's also given over here in the runtime status of the program. So basically I have extracted the turn on voltage for the diode and also the on off current ratio for the diode. And now I also want to show you an example of a MOSFET. And I don't want to go into the details of how to construct the structure of the MOSFET. I've already shown it in another video. Let me direct you to that video. Here is a video. It's a Silvaco TCAD basic introduction and tutorial on MOSFET based on Athena and Atlas.
Sir, are you still on the fence with
discussed how to construct this MOSFET structure. So I'm not going to go into the details of constructing this structure. I will just show you that part where I have extracted the turn on parameters, the threshold voltage for the MOSFET and also the on-off current ratio for the MOSFET. It's given over here where I have fixed the drain voltage at 5 volts and I'm running a sweep for the gate voltage from 0 to 1 volt with a step of 0.02 volts, and then I output this the log of this file with the name of MOS4. Okay, I Tony plot this log, and in order to extract the threshold voltage and the on-off current ratio, I input this log file. For the threshold voltage, we find the x-intercept of the maximum slope of the gate voltage versus the drain current. And for the on-off current ratio, we find the maximum of the absolute of the drain current versus the minimum of the absolute of the drain current. Or we can say the maximum of the magnitude of the drain current and the minimum magnitude of the drain current. So the ratio of these two. So I'm going to run the simulation now. Here is the structure, and while the code is still running, I'm going to close the diode part now. We can look, for example, at the net dopings across different regions for the MOSFET structure. So as we can see, this is the drain region, this is the source region. Here is the gate region, here is the substrate region, and I'm going to click on display in order to look at different contexts. So I click on, I'm going to minimize this as for now. So I click on contexts and then I hit on apply. So now you see we have the gate contact over here and the drain contact and the source contact and also the substrate contact. I'm going to minimize this and let us look at the initially at these curves. I hit on apply. In fact, let me disable the asterisks or the stars. So So here are the IDS versus VDS characteristics for the MOSFET. So initially I've set the gate voltage to 1.1 volt, and then we run a sweep for the drain voltage in the range of 0 to approximately 3.3 volts. And then I've set the gate voltage to 2.2 volts, and we look at the IDS versus VDS characteristics. And then I've set the gate voltage to 3.3 volts, and we look at the IDS versus VDS characteristics. But we are more interested in looking at the IDS versus VGS characteristic, which is this one. Let me disable the stars. Excuse me. So from this IDS versus VGS characteristic, we can see that here is the maximum slope region. And when we extend the maximum slope region onto the x-axis, we see that the x-intercept would be around 0.4 volts. And we can also see that in the runtime status of the program that our extracted threshold voltage is approximately 0.43 volts, or we can say 430 millivolts. And we see that in MOSFETs that the threshold voltage is around that range for actual MOSFETs as well. Also, in order to visualize the on-off current ratio, we need to look at the semi-log IV characteristic. From the semi-log IV characteristic, we see that the drain current is in the range of approximately 10 to the power of minus 10 to approximately 10 to the power of minus 4, or we can say approximately 6 orders of magnitude rectification. Or here we can see that here is the extracted on-off current ratio for this N-type MOSFET structure, and the on-off current ratio is approximately 5 into 10 to the power of 5. Okay. Now I want to show you another example which is based on a thin film transistor. Here is the code for the thin film transistor. So for the thin film transistor, our dimensions in the x direction are from 0 to 35 micrometers, and along the y direction, the structure is running from 0 to 0.12 micrometer. And we have smaller dimensions in the y direction because this is a thin film transistor. Then region number 1 is amorphous indium tin zinc oxide, and we actually introduced this material is not a built-in material inside Silvaco TCAD, so it's called a user-defined material, or we have defined a new material inside the Silvaco TCAD software. And also I have a video on how to include a new material inside Silvaco TCAD software. Let me direct you to that video as well. Or let me go back. So here, and then we go to videos. Here is the video, how to introduce a new material in Silvaco, Atlas tool of Silvaco TCAD.
Whatever you do, it's better with...
I'm not going to go into the nitty and gritty of how to include a new material in Silvaco TCAD, but amorphous indium tin zinc oxide is not a built-in material, so it's a user-defined material. So we have this line of code, and then these couple of lines of the code for introducing amorphous indium tin zinc oxide. We introduce its dimensions, and then we introduce its parameters over here: the band gap, the electron affinity, permittivity, density of states in the conduction band, density of states in the valence band, electron mobility and hole mobility, etc. And region number 2 is silicon dioxide. And its dimensions are also given over here. Then we define the contacts. Then we define work functions for these 3 different contacts, for the gate, for the source, and for the drain. We have defined the band gap and the permittivity for the silicon dioxide material. Then we plot the structure, we introduce models, and we introduce defects inside the structure. And then I have fixed the drain voltage at 5 volts, and I'm running a sweep in the range of -1 to 4 volts for the gate voltage. And I've saved this log file with this name. So in order to extract the threshold voltage and the on-off current ratio, initially I have to input this file over here, and then I use extract name VT, and then we find the x-intercept of the maximum slope of the gate voltage versus the drain current in order to determine the threshold voltage. And in order to extract the on-off current ratio, we have to divide the magnitude of the drain current, of the maximum drain current, divided by the magnitude of the minimum drain current. So let me run the simulation over here. Here is the structure of the thin film transistor, and I click on this icon in order to look at the contacts. So we see here is the source contact, the drain contact, here is the source contact. As opposed to the MOSFET, where we have a silicon gate dioxide over here, and on top of that we have the gate contact. We have the gate contact over here for a thin film transistor, and here we have an insulator region based on silicon dioxide, and then this is our semiconductor region, which in this example is amorphous indium tin zinc oxide. And while this simulation is still running, we can look at the energy band gap of this structure. So we go to tools, cut line, draw a cut line over here, click on this region, display. The plot is ready, but let me finish plotting the energy band diagram first. So you click on AC of T, EV of T, electron quasi-Fermi level, hole quasi-Fermi level. I hit on apply, and here is the energy band diagram of the structure, where for the amorphous indium tin zinc oxide we have the energy band gap around 3 electron volts, and for the silicon dioxide the energy band gap is around 9 electron volts. Now, since we are more interested in looking at the threshold voltage, so for that purpose let me do this. Okay, the maximum slope is around this region. We extend a line from the maximum slope region onto the x-axis, and the turn-on voltage is around 1.6 volt, and this is the exact extracted threshold voltage for this thin film transistor, which is 1.66 volts approximately. Also, in order to visualize the on-off current ratio, once again I look at the semi-log IV characteristic for this thin film transistor, hit apply, click OK, and now we see that the minimum current is approximately 10 to the power of minus 16 amps, and the maximum current is around 10 to the power of minus 6 amps. So we actually see an approximately 10 orders of magnitude rectification. And once again, for some reason the program has exited. So I'm gonna quickly run the simulation once again. Run the simulation. So there is approximately 10 orders of magnitude rectification in this thin film transistor. So we can say that the on-off current ratio for this is approximately 10 to the power of 10. While the code is running, we can once again look at the contacts, the drain, the source, and the gate contacts. We can look at the meshing inside this structure. The meshing should be denser around the interface region, and we can define less dense meshing. So in this structure, the meshing is not really optimized, but we can optimize it. We like use denser meshing inside all regions, but the way we can optimize it by introducing denser meshing around the interface and less dense meshing away from the interface in the regions which are less critical for this structure. So here we see in the runtime status of the program that the threshold voltage for this thin film transistor is approximately 1.66 volts, which we can also visualize from extending the maximum slope onto the x-axis over here. And the on-off current ratio is 4.85 10 to the power of 9, or approximately 10 orders of magnitude rectification for this transistor structure. Or we can say the on-off current ratio is approximately 5 into 10 to the power of 9, which we can also visualize from this semi-log IDS versus VGS IV characteristic. So this is how we extract the on voltage for a diode, the threshold voltage for a transistor, and the on-off current ratio for both diodes and for transistors. I hope this video was informative for you, and I will see you next time. Take care. Adios.